Hi ladies, Saxon Advanced Mathematics, Lesson 11. My video stopped abruptly last night, so I'm finishing the lesson today. I believe that we were just wrapping up problem, or example, I should say, 11.1. I think that problem was done. Let me know. I'm just going to move on to the next example. Let me know if you have any questions about how I finished that. Okay, so example 11.2 looks like this. We have a circle with an inscribed quadrilateral, completely irregular shape. Looks kind of like that, wobbly edge. And this is the way John's written the details. And we'll decode these once we get the figure copied. Okay, I'll give you a second to catch up. Our job here is to solve for x, y, and z. You can do them in any order, but I have given you the advice before, I believe. Oh, excuse me. I always yawn once I start talking. Alphabetical order is a great way to go. You don't have to do it that way, but that's a good way to just tackle these problems. So I will do it that way. And I look at x here. This x represents the measure of that angle. And I remember that any two opposite angles in a quadrilateral add to 180, an inscribed quadrilateral, I should say, meaning that it's a quadrilateral written inside of a circle. So I know that x plus 80 must equal 180. I visually subtract the 80 and I get x equals 100 degrees as my first answer. Okay, that's correct. I move on to y. I see that y works the same way. Y is this angle. This angle is the one opposite it in the quadrilateral. Those two will add to 180. And I visually subtract that, and this time I get 105 degrees. Also correct. Okay? So far, so good. Z is not one of the interior angles of the quadrilateral. Z represents this inscribed arc, going from this point to this point. That's not super clear. You have to understand that about the diagrams. And then this 50 degrees represents from there to there. So we've got an intercepted arc. Let me grab another color. We've got an intercepted arc. We've got two pieces of information about the intercepted arc that goes all the way from there to there. So if we could find the length of that arc, then we could solve for z. So I look at, well, wait a minute here, look. This angle here has the same endpoints of that intercepted arc. So we know that the intercepted arc is twice the inscribed angle, so we know that 50 plus z has to equal 2 times 80. Does that make sense? There's the angle, there's the intercepted arc. The intercepted arc is twice as big as this angle, which is 80 degrees. All right, and then we just do a wee bit of algebra here. This would be 160. So we'll subtract the 50 from both sides, and we get z equals 110 degrees. Yay, that's right also. Just a word about showing your work. I'm fine when it's super simple, something like this. I didn't bother to show the minus 80, minus 80. I didn't show the minus 75, minus 75. I'm okay with you mentally doing some of those really simple steps. I will just say that on a test, if you just accidentally did your mental subtraction wrong, I couldn't give you as many points if you didn't show me exactly what you were doing. If you just said x equals, 75 and just made a crazy mistake, I couldn't give you the point. If you showed me the subtraction, then I could, because I would see, oh, that was just a silly little mistake. So your choice, but I am okay with you skipping some of those really obvious steps. Example 11.3. This time we have an inscribed triangle. And we have X, Y, and Z. Those all have degree markers, so we know that's the measure of the inscribed arc with these as the dividing points. It helps me to draw these in. It helps me see what I've got. This is 35. And this is 75 degrees. Okay, so we're to find X, Y, and Z. Well, we see we've got this same pattern where we can take an inscribed angle and know that the intercepted arc is double. That's going to be fine. Let's see, we can do it really fast. We can do X equals, again, I could write 2, well, I'll just do it. 2 times 75, right? Because X is twice this angle. So that would be 150 degrees. And Y, okay, there's the arc. So this is the angle that's creating Y. Y is going to be equal to be 2 times 35 degrees, which is 70. Z, we have a problem because we don't know the measure of this angle that creates that intercepted arc. However, it's really easy to find it because we can either find this angle by saying, okay, 75 and 35 is 110, so this must be 70. And so then Z equals 2 times 70, which equals 140. Or the other way we could have done it is by taking advantage of the fact that these three numbers have to add up to 360. Let's just check and make sure that they do. 12 plus 4 is 6, and carry a 1, 360. Okay, so that works. We could have, if before we calculated this way, we could have said 150 and 70 is 220. Subtract that from 360 and we get the 140 that way. So either way, that would have worked, but those are all the right answers. Yay! All right, number 4. This is our last one before we stop talking about circles and go to our second topic. Example 11.5. Here's a picture. There's a circle a little bit to this end of the line. And they're impossible to draw perfectly, but we've got some tangents here. Okay, ignore that. The triangle and the circle are tangent at 3 points as shown. So it would be there, there, and there if I had drawn it with precise geometric precision. Now we have these segments labeled all around it. Okay. Giving you a chance. This is wrong. This should be X. These are both X. I'm just double checking for accuracy. Okay. So we're looking at this picture and we sort through our brain to try to find what are some properties that would allow us to solve for X and Y. And when we have tangents, one of the things we remember is that when two tangents hit a circle from a point outside the circle, the length of those tangents is the same. Okay, now my picture doesn't necessarily reflect that, but in this case, we can say that x plus 4, this length, is equal to 6, this length. And again, I can do the mental subtraction and I can say x equals 2. Notice this time it's not a degree measurement. We're not looking at angles. We're looking at length of segments. Okay, so there's one answer. And then I can go over here and go, okay, x plus y equals 10. And I know that x is equal to 2, so I can say 2 plus y equals 10, and then that gets me to y equals 8. Yay. This is kind of a red herring because that information really doesn't tell us anything. We know that they're equal to each other because it's coming from another point outside the circle, but that doesn't give us any information to solve, but that's okay. We have what we need, and we've solved. Okay. The next part of this lesson is another one of those juicy topics that when people think about algebra, this is one of the key topics, the quadratic formula. We know that there are several ways to solve a quadratic equation. And I'll remind you of what that is. There are 3 ways to solve a quadratic equation, which is something that looks like this. This is the standard form. Okay, we call that the standard form of a quadratic equation. It's got an x squared term, an x squared term, a plain x term, x to the first power, and a term with no x, or x to the 0 power, because anything to the 0 power was equal to 1. So we can think of it that way. But this is the standard form, and by solve, I mean we want to find a value for x. The first way we learned how to do it was by inspection. We would just look at it, and we would come up with 2 numbers that would multiply to c and add to b, and we could use those numbers to create our solution. That was fun. That works out really well when x is an integer, a whole number or a negative whole number. That's what integers are. The second way that we learned and just reviewed was by completing the square. And that solution we found is good for that strategy is good for all values of x. X doesn't just have to be an integer. Anything will work. Any quadratic equation can be solved by completing the square, which is great. However, what happened is that back in the day, there were some mathematicians, I believe in the 1700s, who said, this works, but it is a long, daunting process with many steps. And wouldn't it be nice if we could just jump in and go straight to the answer without having to do all of that drama? So what they did was they developed a formula that basically takes you from step 1 to the last step of completing the square without having to go through all of those steps. So we call that by quadratic formula. And that is x equals minus b plus or minus the square root of b squared minus 4ac, and then the whole thing is over 2a. Uh-oh, my pen's starting to run dry. It's always a sad day when I have to switch colors. But you guys are always green because your book is green, and it helps me keep everything straight when I'm posting videos if I can tell by the color of the writing which class it is. All right, let me see if this green is dark enough. All right, so what we're gonna do first is we're going to take the standard form of a quadratic equation, this, and we're going to complete the square on it, and we'll see that that's how you get this equation, okay? So we're going to link this all together by taking this, completing the square, and seeing that that's how they got quadratic formula. It isn't just made up out of thin air, although sometimes it looks like it. I will also tell you that back in the day, I had a student whose name was Zach, and he loved to draw dragons. And so this was when we were meeting at the school that is now Edmonds Heights. And my students were waiting for me at the beginning of class. They came early because they had lunch and they sat in there to eat their lunch. And we met right after lunch. So they'd already been there for a while. And Zach had been drawing on the whiteboard, as one does, and he drew an amazing picture of a dragon. He was a really good artist. And he drew this dragon, and it was breathing fire, like this. You know, he made like way more involved and detailed, but instead of it just being a speech bubble, it was all in oranges and reds, like fire. And we were talking about, oh, what would the dragon say? And he decided that the dragon would breathe he thought that looked like something that would come out of the dragon's mouth. The dragon would breathe the fire of the quadratic formula. So we started calling the quadratic formula the man-eating dragon. Oops. Okay, I will very often call it that, and it just conjures up that memory for me of Zach and the cool picture of the dragon and the way he thought that the formula looked like something that would come out in that cloud of fire. Zach is now, how old is he? He's like 29 or 30. He is married. He has a baby girl who I think she's a year old by now. And he lives up in Mount Vernon, and he works for a seed company and helps develop new strains of seeds that have desirable characteristics. Last time I talked to him, which was about a year ago, he was working on making new strains of broccoli. So there's a little story about a former student. All right, so what we're going to do is we're going to take the standard form of a quadratic equation, and we're going to complete the square on it and see what our answer looks like. So the first thing we would need to do is divide away that lead coefficient. All right, so then we will get x squared plus b over ax. And I'm gonna kick this to the curb in the same step. So then we have a gap there, and we have minus c over a. We're gonna calculate our magic number. It's going to be b over a, times 1/2 squared. I draw an arrow to what's inside because that's useful to me. And so it's going to be b over 2a squared. So this is going to be plus b squared over 4a squared equals, we have to do it to both sides, right? Okay. Now we're ready to see what our perfect square looks like. I'm going to write them both out. This is going to be x plus, and it's the number in here, it should be b over 2a. All right, these two should multiply together to give us this, and that would be b squared over 4a squared, check. And they should add together to this. The denominators match, so we can add them. It would be 2b over 2a. The 2's would cancel, so that's correct. So yay, I feel good about that. This we have to fix so we can add it. We're gonna have to multiply this by 4a in order to get matching denominators there. So this, I'm gonna switch the order of this because I have a minus sign here. When I add it, it's going to be b squared minus, and then it's 4a times c, so I'm gonna write that alphabetically. And it's all over 4a squared. Okay, that's a little messy, but all we had to do is adjust the denominator on this one, and then we can add them. All right, This I'll rewrite as a perfect square rather than showing the two binomials separately. This is all the same. Now we want to take the square root to get rid of that. And now we have, these cancel each other out, so we have x plus b over 2a equals, and then we're going to have plus or minus. The top is going to stay inside the pig house, b squared minus 4ac over this. We can take a square root. The square root of 4a squared would be 2a. Right? Oh, the sun is getting my page. I'll move it after I finish this. Now we subtract this from both sides. And look what we've got. X equals, I'll do the denominators first. I mean the numerators first. Minus b plus or minus the square root of b squared minus 4ac. And the whole thing, matching denominators, is over 2a. That's it, you guys. That is the man-eating dragon. So we did it. We took the standard form, we completed the square, and we got this fabulous man-eating dragon of a quadratic formula. What that means is that we proved that you can use this as a shortcut for completing the square. So now that we proved it, we can't, that isn't technically a proof though, that's just a calculation. We have one problem to do, 11.6, that just reminds us how to apply it. And I'm gonna move out of the sun just a little bit because I know it distorts the light for you when you're viewing. Okay, this is our last example. It's 11.6. It says use the quadratic formula to find the roots of the equation and remember that when John says find the roots, that's just another way of saying solve for x. Okay, so there we have our quadratic equation. It is in standard form. I like it. It's all organized and clean and it's in the right order. So that's great news. And I'm going to remind us that that's the form. So we can easily see where these lead coefficients are going to be the values of A, B, and C. So we make ourselves a little chart. I insist that you write this down. Remember, the sign is part of the value. So this will be 3, B will be minus 2, and C will be 5. Some students like to take extra care and put that sign in front of all the values so that it's crystal clear. I'm not against that. I think that's a great idea. Then every time you work one of these problems, I want to see you write down the quadratic formula again, unless it's already on the page. If it was already on the page, I would be okay, but mine is not. So I'm going to write it down. We just proved that this is right. Okay, now we're getting ready to plug in our ABC values here. Remember that it is vitally important that we use buckets. If we don't use these, it is beyond easy to mess up your calculation, especially when you have negative values over here. So just don't even worry about it. Just make the buckets every time. And I always tell this story. You guys may or may not know Isabel Smith of the Smith sisters, who all were my students and have since graduated and moved to Texas. Isabel was one of those students who was taking classes with me, but also finishing up her classes with Nancy Chang at Edmonds Heights. And she and I had already covered this calculation, and I talked a lot about how important the buckets are. And then she was in her other class, and Nancy was teaching them this process as well. But Nancy did not stress the importance of using buckets. And she put a problem on a board and she was working it through with the class and they got the wrong number. And that happens to all teachers. by no means am I trying to humiliate Nancy because she's a great friend of mine and a wonderful teacher. But she was having one of those moments where she couldn't figure out what she did wrong and the whole class was confused. And Isabel sat at her desk quietly working the problem with buckets the way I had taught her. And she got the right answer, or she got a different answer. She raised her hand and said, Nancy, is the answer, whatever? She shared the answer, and Nancy said, that's right. How did you get it? And Isabel, who wasn't always the strongest math student, so this was a huge victory for her to get this problem right, because she was not the student who was normally showing the teacher her mistakes. That was not the role she usually played. But she had a big smile on her face and said, I used buckets, Nancy. That's how I got it right. And she told me that story, and I was so proud of her. So whenever I talk about buckets in the quadratic formula, I think of Isabel. Okay, who has since graduated from college, right? All right, so let's fill these in. B is equal to minus 2. So here I put minus 2, and here I put minus 2. A goes in this slot. A is equal to 3. And A also goes down here. And then, oh, I'm sorry, I did something wrong. The 4 should go first. It doesn't need a bucket, but I already put one, so I'll just do it. This is where the A value goes. And then the C goes there. Okay, so this wouldn't need parentheses. I'll just leave them for now. But I got carried away with my buckets, didn't I? Okay. So we're going to do a little bit of cleanup before we write it again. I like to simplify what's inside the pig house before I drag the numbers down to the next stage. So minus 2 quantity squared is positive 4 minus, and then we can multiply all these together. 5 and 4 are 20 times 3 is 60. So this is going to be a negative number, isn't it? 4 minus 60 equals minus 56. So that's the number that's going to go in here. So I'm going to write this again, and I can simplify my other parentheses. 2 negatives make a positive, so that's 2 plus or minus the square root of negative 56 all over 6. That looks really good so far, doesn't it? We got that whittled down to something very manageable. And our last step is to look and see if we can factor and cancel anything. And I get excited because I see a 2 and a 6 here. Those are both even numbers. So it looks like we might be able to do something there, but there's no coefficient in front of the radical sign. But that reminds me, well, maybe I can simplify 56. And I get real excited because I know that's going to be 8 times 7. See how I do my prime factor tree off to the side here? 8 is 2 cubed. So there are my prime factors of 56. I can pull a pair of 2's out, and I'll have 14 left inside. So I can write this as 2 plus or minus 2 square root of 14 all over 6. And then I can't cancel this yet because I'm adding here and subtracting, fancy. But I can factor, just write that. I can factor my numerator like this. I can pull 2 out of both terms, and then I'll have 1 plus or minus the square root of 14. And then that's over the 6. Now I can cancel because I'm multiplying this 2 and not adding it. So that cancels, that becomes a 3. And then for my final answer, we just want to write this as 2 separate fractions rather than combined. That is a slightly neater and cleaner. Oh, wait. This was minus all the way along, so it's got an I on it. I forgot that, right? There's a minus 56. So I simplified here by pulling that minus 1 out and stating it as an I. When we have a complex number, which this is because it's real and imaginary, we always want to do that complex number presentation and separate the 2 pieces. So that's why this is the preferred format for our answers. And that's correct. Yay! Finally, the end of lesson 11. Enjoy, have fun with those circle problems. I hope you love the quadratic formula even a little bit, because I love it a lot and I'm excited that we get to use him again. So I leave you now to your homework. Thank you very much and goodbye.